Talented. Yes. I think it starts to be the time. Everyone remembers this is a serious event, 100% serious. We've had no time to practice. Actually, we try to be somewhat right, but obviously we won't be. We try to offend as many people as possible, as is the way in today's world. I think that can go now. I'll briefly give you the structure of today's debate. We will start with introductions. We then go from topic to topic. After opening statements, we have point, counterpoint. Me being the host here, I'll represent computed tomography, and I'll go first, and Mikko can then answer. We will be making final pitches, and then we have audience vote. So everyone here has to be listening. Let me introduce you, the contestants. Here is Professor Mikko, the relaxation nation, Nissi. He's an MRI maestro from here. Mikko leads the charge in preclinical quantitative MRI at University of Eastern Finland. Whether it's swift imaging, virtual histology, or taming ultra-short echoes, he's got a sequence for it. With AI on his side and a 11.74 Tesla micro MRI in his pocket, he's here to prove that when it comes to imaging, relaxation matters. Mikko's motto is, good things come to those who speak.
And in the white corner, you all already know Dr. Janne Mäkelä, the contrast whisperer, academic research fellow, master of contrast and cartilage. Janne leads the CT imaging group at UEF, diving deep into joint degeneration and all things nano. Whether it's photon counting CT on someone else's scanner, thanks Oulu and Sweden, nano agents developed elsewhere, cheers Boston, or making visco supplement sweats, thanks companies, he brings surgical strategy and just enough sarcasm to keep things fun. The guy runs a CT empire without even owning the throne. And Janne's motto is, contrast is high, the budget is not.
Next, we will introduce the technologies. I don't think I need to dig too deep into this specific technique and its technicalities. CT is quantitative by nature. Attenuation equals density, right? However, in reality, let's all remember that attenuation is a bit complex process. Where can I get the pointer here? Yes. So both the photoelectric and the Compton effect, yeah, they vary depending on both atomic number and X-ray energy, which means quantification isn't necessarily always straightforward.
Straightforward.
So yes, it's quantitative, but it comes with a footnote.
Right. And since you are all familiar with CT, I'll try to go through the theory and background of MR imaging, which might be less familiar to you, in a single slide. So here we have
55 minutes.
a possible imaging target in the magnetic field with a scanning coil around the target volume. And in such an external field, there's a phenomenon that results in what is known as a net magnetization. So we can imagine that each and every voxel in the target has such group of spins slightly aligning with the field, producing net magnetization. And this is the thing that we play with. And that has some properties. So in the background, we have the coils. They have their sensitivity profiles in the spatial, wherever they are distributed. And then the target itself has some physical parameters tied to it. And these physical parameters are things like T1, T2, T1 row, MT, and so forth, all kind of MR measurable physical properties. And then at the end, we have some data collected for each of the receiver coils. And these are collected in frequency domain, not in spatial domain, but in frequency domain. And this is known as the K-space. Right? And there's an equation describing how the scanner functions as a projection from the physical parameter space to the data space that we collect. So during an MR scan, which is a complicated process, not unlike playing a piano and trumpet and trombone and whatnot at the same time at various intervals. So we apply frequencies to the target with the coils, and via that, the signal evolves in the target during the scan. And that can be represented by these tiny images that look slightly different. Then we have the coils and their sensitivities. These are multiplied. So each coil senses some part of this physical parameter and how it evolves because of how we play our instrument. And then during that time, there would be full data available, again, in the frequency domain. So all encoded in spatial frequencies, not in spatial locations, but spatial frequencies. And out of this full data that would exist in the scanner, we collect something with our sampling operator, which then gives us this tiny fragments of the data that would exist if we had infinite time to collect it. And then from that stuff, we solve for these physical parameters that are quantified then. Or we could solve for these images as they appear during the sequence. All right, so that's the basics of MR.
There are still people awake. And now we will be giving our opening statements. First of all, why CT rules the game? Lightning fast scan times, whole volumes acquired in seconds, perfect for high throughput imaging or impatient users. It's cost effective, especially compared to MRI, whether clinical or lab-based, these are generally cheaper. There's availability from hospitals to research labs to airport security. CT is everywhere and everyone knows how to use it. Exceptional spatial resolution. If you want structural detail, CT delivers with crisp, high contrast edges. Like I mentioned, quantitative by nature. Hounsfield units offer standardized, reproducible density values. No need to guess what a bright spot means. Material versatility works beautifully across biological, industrial, archaeological, electronic samples. As long as it attenuates X-rays, CT's got your back. 3D reconstruction, it's standard, not special. Segmentation rendering are routine, not just an afterthought. Minimal sample prep, whether it's wet, dry, messy, CT doesn't care. It's perfect for dense composite materials from bones to batteries to bricks. If it's solid, CT will slice it.
Did I hear you say segmentation is natural? Is it because of the black and white contrast you have?
I'll hold my thought.
Right, so for the MRI side part, we don't just show the structure, but also give some quantitative information about it. And it's not just black and white, bone or no bone, but soft tissues, different types of soft tissues, minute variations between soft tissues. Water content, is it like air or is it like water? Is it visible? It is highly visible, and the amount of water is also visible. And we may look at molecular mobility, tissue composition, soft tissue composition, and what was it? Radiative something, radiation dose. We just heard the plant, the flower, not even a biological. I guess plants are biological living creatures, but without a matter. So maybe we don't worry that much. But the poor flower died on the CT scan. How do we dare even put living animals into a scanner? So how about perfusion and flow imaging, functional imaging of tissues as they, let's say, heart pumping blood around, or do we just cook that blood? Relaxation times, they are sensitive to something else, something more meaningful tissue properties. So unlike CT, not serving the results smoking hot.
Now we get to our first round, talking about resolution and speed. Now this table here, it tells a very clean story. Scan times have come down, resolution has improved, reconstruction has gotten faster decade by decade. But sure, if we're being completely honest, this is extremely simplified timeline, and these numbers are more like marketing era benchmarks than universal truths. For example, in the 80s, 90s, slice thickness varied wildly depending on the scanner model, and the reconstruction times weren't just hours. They could span overnight or longer for large data sets. In the 2000s, yes, we had 64 slice CT, but you still couldn't always rely on sub-millimeter isotropic resolution in real clinical settings, especially not without heavy dose or perfect patient compliance. And even today, in the 2020s, while 0.25 and below millimeter resolution and sub 5 second scans are technically achievable with photon counting, that doesn't mean they're routine or that image quality is uniform across the field of view. To talk about the resolution first, I'll just completely skip micro CT and jump immediately synchrotron nano CT, because let's be honest, that's where things start to get wild. This study, published in 2023 by a team at the Shanghai Synchrotron Radiation Facility, showcases full field hard X-ray nanotomography reaching sub 50 nanometer resolution in 3D. That's not microns. We're talking tens of nanometers here. That's a resolution boost of over 10,000 times compared to your average clinical CT, working in the hundreds of microns. And what is especially impressive is that they simultaneously used phase contrast, which allowed them to image low Z materials like carbon and polymers, materials that are notoriously tricky for conventional X-ray. Then talking about speed without giving up resolution, this study by Veldle et al. Is a brilliant example of what modern photon counting CT is capable of. The team scanned human cadaveric pelvises and upper legs using 9 different scan protocols, gantry rotation times changing, and 3 pitch values were used. Their fastest scan clocked in at under 4 seconds. So that's a full high resolution acquisition in the time it takes to take a deep breath. What's interesting, maybe a bit surprising, is that the fastest scans were actually rated as having the best image quality, even though objective metrics like noise were somewhat worse. Why? Because, for instance, streak artifacts, especially around metal, were dramatically reduced. And that then had a bigger impact on radiologist perception than just raw sharpness or SNR, signal to noise ratio. Going back to what I discussed earlier, it's not necessarily about the image quality. But yeah, it's not just about signal to noise ratios. It's about how clean and interpretable the images are. Now, streaking can still be a problem, and I'll come to that back later. But here's the kicker: we can still scan metal.
Yeah, I gotta give you that. MR has trouble scanning metal, that is for sure. And I also have to give you the 50 nanometer resolution. I'm fairly confident that I can say that MRI will never reach 50 nanometers, but only fairly confident.
Never say never.
Never say never. Like 640 kilobytes of memory was always enough for anything you ever need. So why settle for slices when you can get material poetry? Well, but I'll have to start with a disclaimer as well. So in MR, and I guess also with CT, the resolution and speed really depend on what one desires, what the SNR should be, and what the quality of the image is up to be. But in MR also, due to the size of the coil that we use for scanning, and there's been a lot of development on image acquisition and reconstruction on MR as well. More and more receive channels, making the problem more and more parallel with more and more signal collected from the target, more and more transmit channels, allowing simultaneous imaging of multiple locations in the sample, and improving the image reconstruction by utilizing the spatial sensitivity variations of the various fields utilized in the scanning, and all kinds of developments for that. Some historical perspective too. So the very first MR image on the left by Sir Paul Lauterbur in 1973 of two tubes of water in D2O or heavy water. So none of the existing methods could differentiate between heavy water and standard water except MR. And thinking of resolution, they had 20 by 20 pixels across this 4.2 millimeter sample yielding resolution in the sub-millimeter category. So pretty high resolution already in the very first MR image. And the same for the next example of a human finger in 77. And then there's been quite a bit of development from the first brain image in 78 to nowadays with higher and higher field strengths, better and better electronics and so forth. So we can already get a glimpse of something that kind of looks like CT image into what MR looks. Well, MRI is kind of slow, I agree, yes. The first papers didn't really describe much in terms of what the resolutions, what the slice thicknesses, the scan times are, but those ranged from 15 to 40 minutes for 2D slice, and it has steadily improved to sub-millimeter slices to sub-millimeter resolution. But maybe as a kind of a reference, a typical clinical scan with reasonable quality amounts to something like 10 to 60 seconds per 2D slice with a couple of millimeter of slice thickness and well below 1 millimeter in plane resolution. Reconstruction times, well, as the computers have advanced, coming down from a long time to seconds or even real time. Maybe looking at what's possible in like the synchrotron CT with really tiny coils, really high field, resolutions down to 20 micrometers isotropic can be reached in less than 1 hour. But of course, then the sample is also tiny because the coil is tiny and then it gets good signal from a tiny sample, but couldn't do such resolution in human scale. So I guess this round kind of goes to CT in my opinion.
It's up to the audience. Yeah. We'll move on to the second round. Soft tissue imaging. Like mentioned earlier, CT might not be famous for its soft tissue imaging capabilities, but let's remember that there are nowadays so many modalities up and coming. This table here shows how computed tomography is expanding its soft tissue game. Dual energy, photon counting, improved contrast by analyzing energy differences. Phase contrast, dark field CT go beyond absorption to reveal edges, microstructures. Edge illumination offers a more practical path to phased imaging, while synchrotron CT remains the research gold standard. And of course, contrast agents, especially nanoparticles, still play a key role in tissue targeting. Conventionally, dual energy CT has relied on two separate X-ray beams or rapid energy switching. But for instance, Philips's Icon spectral CT takes a different kind of approach. It uses a single X-ray tube and a unique dual layer detector. The top layer captures low energy photons while the bottom layer detects then the higher energy photons that pass through. We're getting smarter imaging. Soft tissue differences that used to be subtle or invisible become more detectable. It's not photon counting per se, but it achieves spectral separation at the detector level, streamlining acquisition without needing separate exposures or source switching. Phase contrast, that has been emerging for soft tissue imaging. Instead of measuring how much X-rays are absorbed, it looks at how they bend as they pass through tissues, offering a whole new kind of contrast, especially for structures with subtle density differences like brain or cartilage. This study here, titled In Situ Phase Contrast X-ray Brain CT, explores the application of phase contrast for visualizing brain structures within the skull, achieving high-resolution images without the need for any contrast agents. And this technique offers a significant reduction in radiation dose, approximately 400 times lower than standard absorption-based CT, while still providing good soft tissue contrast. If phase contrast lets us see edges, dark field CT goes one step further. It visualizes the microstructure itself. This 2022 PNAS paper showed that dark field isn't just a lab toy anymore. It can now be scaled for human-sized imaging. The key is this: instead of looking at how much X-rays are absorbed, dark field detects how they scatter at small angles inside the tissues. That subtle scattering produces contrast even when the tissue looks invisible on a standard CT. On the right, we see what makes it work. A system of precision aligned gratings that capture how the X-ray wavefront is altered by the image. On the right now here, you see the same phantom scanned with conventional CT on top and dark field CT on the bottom. In standard CT, soft materials like powdered sugar and dry wool all look similar. There's barely any contrast. But in the dark field image, their microstructures light up. Scattering makes the difference visible. So even when CT sees nothing, dark field sees structure. Or maybe we create this sugar-coated metal nanoparticle, let cartilage cells, i.e. chondrocytes, eat it and differentiate live cartilage from dead cartilage. These are our preliminary attenuation, phantom, and toxicity results, which we will be presenting later in South Korea. And while we are excited about the potential, we're being careful not to show too much efficacy data just yet for, let's say, intellectual property preservation purposes. But there's another major advantage: spectral resolution. Unlike MRI, where most contrast agents just blur together, CT, especially now photon counting detectors, can distinguish multiple agents in a single scan based on their unique energy signature fingerprint. This study from Petri here demonstrates that power. We used a dual contrast strategy with tantalum nanoparticles and iodine to assess cartilage health. By combining the iodine signal which reflects tissue porosity with the proteoglycan specific health reflecting signal from charged tantalum particles, we improved correlation with proteoglycan content and did so 12 hours earlier. And CT is improving also in 3D histology. Digitalization of museums was mentioned. CT enables micrometer scale resolution beyond MRI. And now contrast agents enhancing tissue specificity mimicking classical stains, and the development on the new agents has been fast. For instance, this project developed at AMC Amsterdam have produced a detailed 3D atlas of human embryos. This atlas is available to all and supports spatial exploration, quantitative analysis of organ growth, and gives clearer understanding of embryonic development. So to conclude, CT has had a glow up. We're now seeing brain, tumors, cartilage, even embryonic structures in ways we never thought possible. It's no longer just for bone. It's not only black and white, Mikko. CT is crashing the soft tissue party with photon counting, dual contrast, micrometer resolution. Let's just say MRI should probably stop looking so smug. CT is closing the gap. But hey, we'll let MRI have its turn now. Take it away, Mikko.
Thank you, Janne. This is all very fascinating. I just started thinking that for CT to improve the soft tissue contrast, we go for the option of adding contrast agents and went as far as mocking MR contrast agents piling up. The thing here is that we don't need contrast agents. We don't need to pierce through the skin to inject some scary molecules into your bloodstream, let alone 2 different types of scary molecules into, or 3 for that matter. No. So for MR imaging, I map hydration, molecular diffusion, and tissue anisotromy like a spa therapist with a physics degree. No worries. For agriculture, food tech polymers, MRI's non-invasive moisture fat proton mapping is huge. We don't kill the plants, nor the humans, nor the animals. And of course, there is this field of medicine that we have heard of, where we sometimes care about the soft tissues, but let's let the images speak for themselves. So here we have an example of a high-quality CT scan of the human brain. And then we have 2 examples of non-contrast MR images of the same subject with, I'd like to think, a little bit higher soft tissue contrast and maybe a little bit more clearly discernible structures between the different types of soft tissues. So with CT, when you say soft, do you mean bone compared to steel or air compared to bone? Remember this image from before with the high soft tissue contrast from the synchrotron, which is not even possible for human use? Maybe. There is some contrast there, yes. How about the mouse? Cardiac, the heart beating as we scan it. That will be a little bit difficult for a CT, I believe. And that's just a crappy example stolen from the net. But here are some more examples of soft tissue contrast, again, without any contrast agents. And these are all stolen from Siemens's image gallery, and the link is down there if it's visible. So you can actually Google it up and you'll find plenty of examples. So these have times attached to them. So for example, this high resolution vascular scan of the brain in 10 minutes for full 3D scan of the entire brain. You could look at it from any whichever direction you want, or abdominal soft tissues, or slightly different contrast for the brain, looking not at the arteries but the venous side of the vasculature, or muscles or fat or cartilage or what have you. Going forward, just by changing, and this is actually not changing during the scan, but retrospectively changing the scan parameters. If the data was acquired properly in quantified fashion, then you can simply modify the contrast that you would get from a scan if you scanned it with in some specific fashion. And again, so this is the same data set, just recalculated using the signal equations, and we can get all kinds of different soft tissue contrasts out of the MR data, while the CT image here shows the bones and the air. And going even further, This fancy image on the left is so-called tractography image, which depicts how the water self-diffuses through the white matter tracts in the brain. So using a sequence that is sensitized to diffusion of water, one can scan tissues and then learn about the anisotropy of water diffusion in these tissues, such as white matter. And then with such images, you can study how the different brain areas are physically connected by the white matter tracts. All right, so that's, I guess, enough for soft tissue.
You are good. I admit it. You are good. Okay, let's get to hard tissue imaging. Rock, bone, electronics, no problem. I was born to quantify that. And apparently soils too. Yeah, this is from Chiang et al. With soil specimens simulating real-world rainfall conditions. Thanks to in situ X-ray CT, they could watch drying dynamics in real time, see how water distribution shifts at multiple scales from individual pores to the entire sample, and map out heterogeneity because no slope fails evenly. And if I noticed some raised eyebrows here, of course I didn't overlook the excellent research coming out of our Jyväskylä FinTomo hub, from real-time 3D swelling measurements to pore scale structural analysis. These studies are great examples of CT stepping outside the typical medical use cases. And when it comes to understanding how soil responds to environmental stress, this kind of work is foundational. What about studying evolution in 3D, made possible by MRI-CT? This study by Ollonen et al. 2024 from Helsinki uses MRI-CT imaging to reconstruct skulls across dozens of vertebrate species and developmental stages. So MRI-CT allows non-destructive high-resolution 3D analysis of bone development, tracking how skull regions change shape, size, and integration over time. The results, an exhaustive data set of mapping the evolutionary dynamics of skull patterning like never before. And now let's crank up the power a bit. This is where metal jet X-ray sources then come into play. Unlike conventional tubes with a solid anode, metal jet sources use a liquid metal stream as the target. That means no melting, even at high power loads. You get more photons, smaller spot sizes, higher resolution. It's like bringing synchrotron level resolution in your lab without needing beam time or a logistics department. So benefits for hard tissue imaging: higher spatial resolution, sharper images, better contrast and signal to noise ratio. You're working with more photons and cleaner data. Higher energy output can push itself into hard X-ray range, and essential for denser materials like metal or geological cores. Then there's also the stability and reproducibility. Liquid targets don't degrade like solids, regenerate continuously, allowing stable long-term scans. Yeah. So researchers at Helmholtz Zentrum Berlin integrated Exilium's sources into their experimental setup at their synchrotron radiation facility BESI 2. So here on the left, we see that by using this gadolinium indium tin alloy, they generate a broad X-ray spectrum. The table here shows by changing the alloy, they are capable of going up to 160 kV, ideal for dense and metallic samples, allowing both diffraction and tomography. And finally, what's really impressive is that it also allowed for imaging of soft matter bones. So sure, metal jet sounds hardcore, but turns out it's just as good at whispering secrets from soft tissue. Metal jet sources aren't just about high energy, high tissue imaging, they're also breaking ground in the soft X-ray range. In this study by Arsana et al., they used half a kilo electron volt beam for soft X-ray imaging with natural contrast, no staining, no labels. Figure 4 here shows how this setup can capture subcellular detail, live cells. And here in figure 6, they used fluorescence imaging to track molybdenum and rhodium nanoparticles in vivo. So using the characteristic X-ray emission to distinguish them separately, one signal for each element. So when it comes to the hard stuff, bone, metal, mineral, or even swelling clay, CT stands for it. High resolution, high energy, high confidence.
I think you got that. Yeah. So for MR imaging, some hard tissues can be scanned, and thanks to so-called ultra-short echo time (UTE) or zero echo time (ZTE) sequences, I can now image bone, teeth, and dried samples. Slowly, yes, but surprisingly well, kind of at least. So the first examples here showing bone specimen scanned with zero echo time sequence, and you can see that there is signal, plenty of MR signal from cortical bone or from trabecular bone. And on the right, there's a micro-CT image from the same sample, and you can neatly see how they align. And then there's something extra in the MR images that is not captured by the CT. And they also provided a high-resolution synchrotron, or whatever that acronym stands for, image of the same specimen. Another example is a teeth scanned with CT and with the MR sequence. And what you can see in the CT is the enamel, which you can't really see in MR. So that's one of the tissues that is a little bit too hard for MR to scan. But on the other hand, you see this softening of the tooth bone underneath the enamel, which is kind of, or maybe not really that well seen in the CT, but MR really highlights the degraded part of the tooth, and of course all the soft tissues around it. You can scan cortical bone and even do quantitative scans of the cortical bones. A couple of examples of different types of, so these are for so-called T1 mapping of MR quantifiable parameter from the cortical bone, and this is so-called magnetization transfer experiment, where again multiple images are acquired from the same sample, and then data can be pulled out from that, such as macromolecular fraction, and then exchange rates between harder and softer tissue pools. Should not go anywhere into detail with that, but as an example of something that bone can be scanned with MR as well. Another example of dental imaging with another ultra-short echo time imaging sequence, SWIFT, and again in the projection or CT-like image of the tooth, we can see bony structures, and that's about it. But with the MR imaging, we can see that there is softening of the dental bone, caries, and some fragments of the enamel, some defects underneath the enamel layer. We can see the soft tissue part of the tooth as well. And another example where a radiograph shows just the hard parts but doesn't show, and the cone beam CT as well, whereas in MR we can see the actual defected part of the tooth, which is completely invisible in the cone beam CT. And by the way, this would be what the standard MR image would look like. So there's quite a difference from the conventional MR imaging to ultra-short echo time imaging. And maybe just to point out, in vivo in humans, cone beam CT, I don't know what these stripy thingies here are, probably some kind of an artifact which we don't have in the MR image. So we can't really see the metal, but we can scan around it. And some more examples of what can be seen with these short echo time imaging sequences, like the coil housings that surround the patient. So these could be used as anatomical landmarks, like wooden structures like pine cone here can be scanned, and even 3D printable plastics produce some signal in these sequences, so we can even scan plastics with MR. And again, a standard MRI sequence here doesn't really show anything but the silicone tube in the middle, which has plenty more signal than the other plastics. So we can do at least something in terms of hard stuff imaging.
We'll move on to quantification and mapping. I scratched my head a bit on this topic, like what could I find? Like it's just that in principle we don't guess, we measure. So in many cases, in parentheses, no calibration phantoms are needed, no relative scales, because HU values are universally defined. You get reliable density maps straight from the attenuation. There's nowadays effective material discrimination available and targeting contrast agents to help in the quantification. Synthetic CTs, they are getting a lot of attention, especially from the AI crowd. But even the most advanced models will still struggle to reproduce what CT gives us for actual physics-based attenuation values. This review here points out that HU estimation is still a major challenge in synthetic computed tomography. Why? Well, first, there's no real physics behind the numbers, just approximations. Second, these methods rely on limited view geometry, so errors start stacking up. And finally, they're often model specific, meaning results can vary quite a lot between datasets or scanners. So while it's impressive that people are trying to turn 2D into 3D into CT-like images, the fact that they are trying at all just proves one thing. CT is the modality everyone wants to become.
Yes, I kind of agree. There are studies trying to turn MR images into CT images for sure. So yes, these people want to become CT scanners. So for MR imaging, as the introductory slide showed, there are these physical MR quantifiable parameters, and these are what we might quantify. So T1, T2, ADC, MTR, DTI, and more acronyms than a typical government agency would have. All quantifiable and mappable. So let's speak about what the process very broadly. So the molecular environments affect the microscopic magnetic fields that the nuclei in the sample experience, which in turn determines how these nuclei behave in the MRI experiment. And the quantifiable parameters that we might be interested in describe this behavior. So something happens in the microstructure that affects how the nuclei behave, and then we can somehow describe how the nuclei behave. So it's somewhat indirect quantification of something that would be physically interesting. But at any rate, here's an example of experimental equine post-traumatic osteoarthritis, where we collected a number of different quantifiable MR parameters from experimental animals and samples and controls, and saw that a whole bunch of these were able to differentiate between the experimental and the controls. Not necessarily saying that one has more, say, proteoglycan, less proteoglycan, more water, less water, whatever the quantifiable parameter tells about, somehow differentiated between these. And then the tricky part might be figuring out what that actually means in terms of, I don't know, Hounsfield units. Another example, looking at strawberry plants, and by the way, no plants were harmed until we finished the protocol and then sliced them up, just for you to see that the intact ones indeed look intact and the infected ones look infected. But already at week 1, we could see, and in these profiles more quantitatively, we can see that there's a statistically significant difference throughout the structure of the plant between the infected and the healthy plants. And we could follow up them live through several weeks and could have planted them at the end of the protocol if we had so chosen. So summarize the quantification. So we have T1, T2, T1 raw, TRAF, T1 SAT, ESM, T2 star, ADC, FAM, TRD, TIDC, and so forth. Many more. Most of these are somehow MR physics related parameters and only reflect the actual material properties or tissue properties in the biological sense. But hey, compared to the Hounsfield units, which really sounds like AU, arbitrary unit, we have a lot of parameters we can quantify. And all of these have really cool method names too. Like here, Despot, Haste, Flash, SIF, Crash, Medic, Grappa, Wipe, Sense, XOR cycle, probably to reduce artifacts, and so forth.
Pure magic. Going to the availability and cost, I did some device spotting around our university hospital. The numbers here show we have about twice as many CT scanners as MRI machines. This reflects a broader national trend. CT scanners are far more widely distributed, not just in university hospitals, but even in Kuusamo. CT scanners, they are smaller, cheaper to install, and require less shielding infrastructure than your MRI, making them more feasible for decentralized locations. MRI still tends to be centralized in larger hospitals, especially for higher field imaging or specialized protocols. Then going on into the pricing, this is real world pricing from Mäkelä, one of Finland's major private hospital networks. You'd expect MRI to be more expensive, right? Given the huge equipment cost, longer exam times, more personnel needed, and so on. But no, it actually seems that CT is more expensive than MRI in many of these listed services. Even contrast-enhanced MRI looks to be cheaper than some CT regions. So I'm just using my imagination here. I'm just guessing. Maybe one reason could be high demand. CT is often used for urgent diagnostics like trauma. So private clinics may price it higher, knowing it's a can't wait modality. Is there a convenience tax? Faster turnaround means more people want CT than MRI. Demand goes up, price goes up. Are private clinics perhaps using older MRI machines? Or maybe since CT scans are more often used in acute diagnostics and routine checkups, they're more likely to be covered by work-related or private health plans. This could give providers then more flexibility to price them higher, knowing that the bill isn't going to the patient. I also checked the Kuopio University Hospital prices. The CT prices are a little lower than MRI. TT was between computer tomography was between 150 300 euros, and MRIs were from 150 to 600 euros. Based on this European review, the total cost per scan are actually almost identical. 177 euros for CT and 180 for MRI, practically a draw. But here's the twist. The cost structure is very different. CT's cost is mostly driven by consumables, especially contrast agents. MRI, on the other hand, burns a lot of money on equipment depreciation and staff time. And that brings us to what I think is the real cost difference. MRI just devours personal time like it's an all-you-can-eat buffet. Let's zoom in on the most time-consuming step here, image acquisition. For CT technician, they spend about 7.5 minutes there. For MRI, 1 hour and 21 minutes. That's 10 times more technician time per scan. It adds up, especially when you think about throughput, staffing, and scheduling. So yes, cost per scan is close, but when you look at how time and resources are spent, CT wins on efficiency. So to conclude, CT scans patients, MRI scans your schedule.
Nothing for that, sorry. Yes, but you pay for what you get, and what you get is magic. Well, but in a real example, the cost of an MRI scanner is something between 2 and 2.5 million euros, including all the bells and whistles of the system and the siting costs, because it is a heavy machine. You need to reinforce the housing and provide all kinds of shielding to keep the magnetic field inside and to keep the RF interference outside of the magnet room. The scans, as Janne mentioned, are something from 200 to 1,000 for the out-of-pocket costs. And what you probably didn't have in your table, there's also an upkeep or service deal, which usually amounts to something like 100,000 per year to keep the system running, or at least promise that the system will be running at all times. So clearly the availability is less for MR, scans take much longer time, and there are less scanners available. And some patients can't even be scanned because of the extremely strong magnetic field. So any implants, well, not any, but many implants can prevent the scan entirely. So you can't bring a person with specific implant in the MR room, even because the implant might twist inside the body, causing tissue rupture and whatnot. Or if it's an active, like an insulin pump or brain stimulator, it might not be compatible for the scan and might, I don't know, do something crazy. And since the bore of the MR scanners tends to be a little bit smaller than in the CTs and much longer as well, a couple of meters instead of a couple of tens of centimeters, claustrophobia may even prevent scanning. But hey, there's no radiation.
Let's get to the actually challenges and artifacts. I decided to change the title. Yeah, for sure, CT still has its fair share of complexity, measurement uncertainty, lack of standards, object limitations, beam hardening and scatter. These challenges remain largely still unresolved. One major limitation now with photon counting detectors is the massive data volume it generates. This must be then reconstructed and moved fast for it to be clinically practical. And I guess we can get to the elephant in the room, the ionizing radiation. Sure. Let's all pretend that we are now surprised. While modern scanners have made huge strides in dose reduction, especially with iterative reconstruction, photon counting CT, we still can't ignore the cumulative dose concerns, especially in younger patients or longitudinal studies. And we've all seen these kinds of studies before, like we have seen these before, like on the left, big promises, bold claims, up to 90% dose reduction. Yes, they are exciting. Let's be honest, real world implementation often lags behind. How often does this actually reach the clinic? But like with making this presentation, AI is definitely changing the game. The real shift, I think, is what's happening here on the right. Not just this one particular study, but the broader trend. AI is already being adopted. Denoising, reconstruction, segmentation, this stuff is actually getting into practice and fast. This review here stated that deep learning allowed up to 80-90% dose reduction without compromising image quality. Canon's AI-CE, that's already in use at our university hospital. GE's True Fidelity, I heard, might be coming into action this year. In 2023, there were almost 700 FDA-approved AI-enabled medical devices, 531 being in radiology. So 531 FDA-approved medical devices in radiology in 2023. In 2021, this number was 17. So 17. So huge explosion there. But of course, we still need rigorous validation all the time. And oh yeah, while we got new tools, AI, photon counting, etc., these artifacts remind us that physics still wins. These artifacts aren't failures of modern tech. They're reminders that imaging is still governed by fundamental physical laws. So yeah, AI is improving. Sure, physics is improving as well. But if the patient can't stay still for 5 seconds, or in MRI's case, 10 hours, none of it matters.
Yes, yeah, we don't want to destroy the rules of physics for sure. Well, challenges and artifacts in MR. Actually, artifacts are the new favorite way of imaging things, and almost everything in MR imaging can turn into an artifact. And the artifacts will confuse you, and only a true master will be able to tell what is an artifact and what is the true anatomy. Same as with CT, the quantification is always some kind of an approximation and a compromise. There's a complex interplay of many influencing factors and lack of standardized tests and procedures and traceable results, maybe even more so than in CT. But artifacts, they are fun in MR and they are plentiful. So let's look at a few examples. Motion artifact, more motion artifact, field distortion metal artifact, some kind of strange ghosting artifact, another even stranger ghosting artifact, field inhomogeneity artifact. On the top image, the transmit radio frequency field is inhomogeneous, and in the bottom field it has been corrected by applying what is known as parallel transmit, and a whole lot of measurement before making it happen, and a whole lot of calculation of the appropriate RF fields that should be transmitted to get the artifact corrected. Some kind of overlap artifacts, another metal artifact blocking quite a bit of the field of view, hip implant, can't really see the cartilage or anything there, so not great. Slight geometric distortion, signal clipping artifact, so signal leaking out from the brain, aliasing artifact that can be corrected with the penalty of excess time spent. That's a strange artifact. I'm pretty sure I don't have such cross inside my head. And yet another metal or susceptibility artifact. And there's so many more. And as a challenge, this came up in the local yellow news yesterday. So it's unfortunately only in Finnish, but cleaning personnel made a
Lethal
mistake. Fatal mistake. Although I don't think this ended up being fatal, but the mistake was fatal at any rate. So cleaning personnel brought a non-MR compatible floor cleaning machine into the MR scanner room, and of course, being heavily magnetizable, plenty of large chunk of metal, the extreme magnetic field of the scanner just whipped that cleaning device into the scanner, and I guess the lethal here refers to the scanner itself. So while no people were harmed, the scanner was destroyed in the process. And that was in Turku, I believe, last week. And there have been similar mishaps every now and then. But
it does happen, doesn't it?
It does happen, but this is due to negligence of the personnel most of the time.
It's always the human.
It's a human error. Yes.
But let's move on to complementarity. I can admit CT gives the structure while MRI gives the story. Like this Euro intervention article states, are we complementary or are we competing? That would make it a nice song. There's growing evidence for complementarity. On the left, a study combining CT and MRI data to improve stroke segmentation. On the right, a systematic review on traumatic brain injury management showing that combining CT and MRI gave the most thorough assessment. Not wanting to go too much into this love story, CT and MRI still, they are rivals, sure, but when they work together, you get something great. Structure from CT, strategy and finesse from MRI, and can't you agree that when they pass the puck between them, diagnosis scores big?
Yeah, not much can be added to that. And here's an example of a specific MR study where we were interested in this bright signal in soft cartilage and whether it comes from the underlying calcified part of the tissue or whether it's in the cartilage. And from MR, we can see that, but where does the signal actually come from? And then we wanted to do micro CT and synchrotron CT to really see what we are looking at. So CT gave us the ground truth and tells us what we are looking at. Extremely useful. Not really about CT, but somehow to say that it would be nice to have a CT on this actually, because I'm pretty sure that we would see these structures and we could compare to MR, but in this case, the plain radiograph 2D image doesn't quite give what we get from MR, internal structures and so forth. But let's not stick there. So I think this is a good final statement for the complementarity.
You have my number. Let's see if we're still friends after the final pitches. Let me just start with this. I don't need to praise CT for this particular audience. Everyone here is already on my side, right? Instead, I'll just focus on this in MRI. So let's talk about this table for a second. It's like a buffet of MRI parameters, all trying so hard to be best friends with everything. Biomechanics, sure. Water content, of course. Proteoglycan, yep. Collagen structure, why not? The problem here, when everything correlates, nothing stands out. It's like showing up to a party and hugging everyone. At some point, you just look clingy. Meanwhile, over on Team CT, we pick one parameter, say Hounsfield unit, and we mean it. It reflects density. It's reproducible. It's not trying to be a wannabe biomarker for every buzzword in tissue characterization. So yeah, MRI gives you 27 maps, 15 relaxation constants, and a philosophical conversation with your cartilage sample. But when you want clear single diagnostic marker that doesn't ghost you after validation, you call CT.
According to one of the leading scientific journals, there's a method, CT to be more precise here, that may cause cancer due to unfathomable mistake, and it's performed 93 million times a year in the US. And it is also confirmed by another leading scientific journal. The common medical scan routinely delivers excess radiation and may cause up to 36,000 cases of cancer a year. And yes, I knew it. You are Dr. Dumogram, the evil ionizer.
I think we have left everything on the table. Given everything now, we'll move on to the voting time. And hopefully everyone was listening very carefully. We want your honest opinion on this, and the answer reflects where you actually listening. So are you ready? Now raise your hand if you now see quantitative MRI as more than just a slow, noisy art project. Anyone who likes quantitative MRI? It's yeah. Many hands raised. But hey, huge thanks goes to my CT team, Mikko's MRI team, who helped us with the slides. PubMed Central helped us a lot, and ChatGPT, who told me he started to feel pretty exhausted. Thank you, everyone. And if I look at the schedule, we are, yes, having the demonstrations there. And with our,
Just crossing.
yes. Thank you.